Okay, in the second video for section 5.4, I'm going to introduce mm, another type of model that employs different types of, actually three types of percolation and growth model. It's called gulling and erosion dynamics model. It is trying to address water erosion phenomena in real world, but it's not that simple. Okay, it's in order to simulate the real world water erosion process, we have to combine three types of models. Okay, so the first part of the model is the fundamental strength of the substrate. Okay, this strength of substrate, how can I say, it prevents the erosion of water. Okay, in order to address this part of erosion dynamics, we use invasion percolation. What's the feature of an invasion percolation process? Do you still remember? It's about the resistance of the environment, right? So every step, um, on the walker, or you can say the front of the percolation, always you always need to choose the cell with the least resistance among all those cells on the front of the percolation, and occupy that cell and repeat this process. So the very fundamental part of this erosion dynamics is about resistance of the environment. Okay, so that's the first part. The second part is seepage weathering caused by groundwater moving through the substrate. We use DLA to address this part. Okay, because the seepage weathering will reduce the resistance of substrate because it's a weathering effect. Okay, and the third part about this model is background weathering. Is another type of weathering, not caused by groundwater, but caused by processes independent of the other two processes. And we're going to use Eden growth model to address this part of gulling and erosion dynamics. Again, background weathering will reduce the substrate resistance. So you can say that invasion percolation is the core and the basis of this dynamic of gulling and erosion dynamics. And the other two components of the model, they are affecting these dynamics by reducing the resistance of substrate. Okay, and yeah, let's say the algorithm. But before that, some variables I need to make clear of. So R is for substrate strength at each cell. It's assigned randomly. You can consider R as the resistance in an invasion percolation. And other parameters include gamma, seepage weathering, and also eta, background weathering. So gamma and eta, they're used to address the strength of two types of weathering. So algorithm here, okay? Seepage weathering through DLA. A random walker is released from an uneroded site or unoccupied site on the ground, on the plateau, and continues walking until it hits an uneroded site neighboring the eroded edge. The value of R in this cell is reduced by a factor gamma. So you can see here we're using DLA to address seepage weathering. The result is that the resistance R is reduced by a factor gamma, and this gamma is decided by the seepage weathering effect. Okay, so this is the first first component that reduces R, reduces what? Resistance of substrate. The second component of the model is trying to address the background weathering using Eden growth model. Okay, specifically, an uneroded site neighboring the eroded edge is selected at random and R is reduced by eta. Again, resistance is also affected by eta, or specifically is reduced by eta. And eta is the strength of background weathering. So two types of weatherings, they are addressed by the first and second component, or by DLA and Eden growth. Their influence on the erosion dynamics is addressed by gamma and eta, the strength of them, and the stronger the seepage weathering, or the stronger the background weathering, the stronger their effect on reducing the resistance of what? Of substrate. Okay, so the third component of the model, substrate weakness where IP, the cell at the eroded margin or front with the lowest value of R becomes eroded. So R here can be considered as resistance. Okay, so IP here is to address the process of eroding. Okay, and we care about resistance because this eroding process will always choose the cell with the least R to occupy. But R can be affected by what? By seepage weathering and background weathering. And these two processes, again, they are addressed by factor gamma and by factor eta. These two parameters, they will reduce the value of resistance. And eventually, what? These two types of weathering will affect the eroding process. Okay, so looks complex because we're using DLA, Eden growth, and IP, three types of percolation and growth models in one simulation. But the logic here is very clear. IP is the basis. DLA and Eden growth, they are used to address two types of weatherings and their influence on IP, right? Okay. On the right side, we have the simulation of guarding and eroding process, and you can find this model in our model library. It's 5.21. And let's talk about the relationship between seepage weathering and background weathering. Okay, gamma and eta. They control the nature of the weathering. If both are equal to 0, then this simulation is pure IP because the resistance doesn't change during this process, right? But if they are not equal to 0 and gamma is larger than eta and they're not equal to 0, they can't be negative, so they must be positive, right? So seepage weathering dominates the process because gamma value, the strength of seepage, gamma value is larger than eta. It means that the strength of seepage weathering is stronger, or you can say the strength is larger than background weathering. Or if it is the opposite scenario, eta is larger than gamma and they are both larger than 0, then what? Then the background weathering dominates the process. This is a very simple but straightforward from what? From hydrology. So let's make a summary of this chapter. So in chapter 5, we talked a lot about different types of percolation models and growth models. Okay, percolation and cluster growth models. They are spatial models derived from either percolation theory or cluster growth approaches. And they have a wide range of applications, right? We talked about the percolation of fire, and we talked about hydrology, right? We talked about epidemiology, epidemiology, and the urban growth, right? And I listed a lot of literature there in this chapter on different slides. If you're interested in them, or you are particularly in a specific realm, you are doing a research or you are carrying out a specific project, you can go to one or several of those literature to go deep along a specific direction of application. Okay, and it's pretty important to know the difference between approaches. Okay, especially between ordinary percolation and cluster growth. Okay, the only the main difference is that history does not matter in ordinary percolation based processes. Okay, but on the other hand, history is important in cluster growth based processes. Okay, in Eden, in Eden growth in DLA, we know that the sequence of occupied cells, of the sequence of occupying cells, or in DLA, the trajectory, the history of that walker matters. Okay, but in IP, it is different. In an invasion percolation process, the cell with the least resistance will always be occupied at each step, which means that in IP, history also matters. But in OP, ordinary percolation, history does not matter. Okay, I think chapter 5 is relatively longer than other chapters we have introduced in this semester, and it's more complex. It's more complex, and even though I think percolation and growth models, they are more important than other models we have learned this semester. Okay, so I would say it's worth it investing more time in chapter 5 and figure out the difference and different methods and different simulation models to simulate percolation and growth processes. Okay, thank you.